We had a problem plotting the prismatic links. So there is one thing that we can do, which is it's a problem with the current version of the toolbox. So what we'll do is we'll reinstall the previous toolbox so that we can do smoothly. So let me do the first thing is I just want to talk about prismatic links. Prismatic link manipulators. And secondly, we want to talk about decoupling. Okay, so to do this, we have a problem with version 10 of the toolbox. Okay, so we'll uninstall that, and what we'll do is we'll install the version 9. Okay. So what I want you to do is go here, go select path depth, which defines the path of the toolboxes. Okay. Go here, and what you'll do is you'll just say delete. There should be a file called path def, P-A-T-D-E-F. Just click on it and delete it. So that will remove the toolbox. That will remove the complete toolbox from the man here. So when we type VER, let's do VER once again. You still have that, but let's exit it. You'll type in exit. Okay, type in exit. It will exit MATLAB. And let's come back again and see if it's still there. Okay, now you don't see. Once you have deleted path def, which defines the path of the toolbox, you won't find MATLAB toolbox in there. Okay. So what we'll do is we'll go here. We'll go to your browser, any browser that you are using, and let's go to once again downloading the toolbox. And here we'll say Robotics toolbox for MATLAB, right? Let's go to downloading the toolbox. And here we'll download the RTB Robotics Toolbox 9.1 because previously we installed 10.1. It has an issue with plotting. So the first link, the second one is documentation. So that is a simple PDF. I would recommend you download that also. But for now, I'm just going to save this as. I'll just save this on the desktop. Okay. 9.10 is what you'll download. Okay, so once that's done, let's minimize this, and here it is. So what I'm going to do is I'm going to extract, and you'll have a folder called Robot 9.10. Okay? You'll just right click on it and extract it. Okay? Fine. Once you're done with that, let's just copy this folder. Right click on it, just copy this. Copy it. Go to your MATLAB and right click here and paste it. Okay, so you'll have, when you right click there and paste it, you should have 9.10 over there. Now what I'm going to do here is this, for that to be recognized in the path so that the software knows there is a MATLAB toolbox, a new one, what we'll do is we'll right click on this and say, go to add to path and select, not paste, add to path here and select folders and subfolders. Okay, so add to path and go to select folders and subfolders. Okay,
I missed it.
Which one?
Previous one.
Just copy the folder here. Copy and paste it here. Okay, so you'll right click and you'll say paste here. copy it from a desktop, paste it here. Then you right click, add to path, folders and subfolders. Okay, so now let me do VER once again. And you should see the robotics toolbox here. Let's see if it's 9.1. Yeah. Okay. So you'll see robotics toolbox, you'll type in VER and make sure the robotics toolbox is there. Good. Okay, so we are all set. What I would like you to do is try the prismatic link code with this, and it should work perfectly with the workspace notation. Okay. So now let's talk about kinematic decoupling. Okay. So we did, yeah.
On the left it didn't have a pad, but it says toolbox 10.4. It's not really bad.
Okay, so if you're using your own laptop, what will have is you'll have remnants of the toolbox. Just do restore path. I can't do it here, but if I do it, it will restore my path. You just do restore path. Okay, so it will, and then you have to do the 9.1 thing. Okay. All right. Now let's talk about kinematic decoupling. Okay, we'll do a inverse. This is an inverse kinematic solution. So this is to find inverse kinematics. Right. So what we'll do here is we have P is given to us, which is x, y, z, phi, theta, and psi. Right. This is given to us. All right, and we need to find the joint variables theta 1, theta 2, theta 3, all the way to theta 6. Okay, and we do this by decoupling it. I gave you a handout. We start off by finding the wrist center. First step is to find the wrist center, right? The first step we do is find the wrist center. Find wrist center. WC or OC. Okay, here the handout I gave you mentions it as OC, so I'm going to use the same terminology, OC. So we start off, we find OC by taking the end effector coordinates O minus D6 times R06 times 001, right? Because D6 is measured along the Z axis, Z5 axis. Now we know how to find R6. R6 is a Euler, or it could be RPY of phi, theta, and psi, right? Once we find OC, we'll do inverse kinematics and so on. So let's take one structure, okay? We'll take one structure and we'll try to find out the inverse kinematics of this. So we'll start off with doing a cylindrical manipulator. Okay, I'm going to start off with a cylindrical manipulator. Cylindrical manipulator with a spherical wrist. Okay, we'll find the inverse kinematics of this. So this is clearly a 6DOF manipulator. All right. So the first step we'll do is we'll set up a DH table for this. Then we'll do this stepwise. Okay. So let me, and then I'll give you a exercise to do for a different manipulator. Let's first start with this one. Okay, I think we have this, so because we are doing the same thing, let me pass this on. This has a DH table. I want you to start setting up the manipulator DH. Here, pass this out. Let me have one. I want you to set up the manipulator in this. First, look at the DH table and set up the manipulator. So now we have
Which one? Go to
Okay.
the MATLAB and just copy it.
So here you have θ1.
Just copy it there. Here, you already have. You need to. This is a British one.
E2.
Or the new one.
This is the new one.
No, the one in the MATLAB.
E3.
This one is the one.
Yeah, you need to remove it first. Just delete it.
θ4. θ5.
Yeah. Close the MATLAB and open it again.
And obviously, this is our wrist center because this constitutes the spherical wrist. These three joints constitute the spherical wrist. Let's assume this
Yeah, now copy.
as your wrist center. Okay? So at this point, what you exactly have is you have three
And
joints.
one. That's it.
At the same point, and from here all the way up to here, it's D6. Okay, from the wrist center to the end effector will be D6. Okay, so let's try to write up the DH table. I have given the table to you, just set it up in MATLAB and see if you have the right configuration. So I'm going to use the following position and we'll try to find the inverse kinematics. Let me start off with a new script. Okay, so basically I'll say clear all. Okay, so what we'll do is we'll start off defining the manipulator, DH of the DH of this cylindrical manipulator. We'll start defining link by link. So the first link will be L1, which is equal to link. Make sure that its link L is capital. Okay, and then we'll have 0, 1, 0, 0, 0. Okay, this is the first link. Similarly, we'll go to the second one, L2, which will be equal to link. Zero, 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 negative pi by 2, and 1. Okay. Negative pi by 2 and 1. Because this is a prismatic joint, so it's 1. Okay, L3. Will be okay, these are the first three joints, and then we have the wrist joints, right? After this, it will be the wrist. So I'm just going to leave a space because now it's the wrist, which is L4, L5, and L6. L4 is this. L6 will have D6, right? So D6 will be theta D A alpha. So A alpha and 0. Okay. So now you can say we'll convert this into a serial manipulator. We'll call this cylindrical manipulator. CYM will be serial link. So it will all combine these links into one manipulator, which is this. Actually, let me remove this. And we'll save this as decoupling. Okay, let's go back here. And okay, so here we have the table. I want you to make sure that the table is correct. Okay, go back to,
Let's go back to the other.
after you do this, run it and check if you get the same DH table that is in your handout sheet. Okay, double check everything. Your handout and your details. Good. All right. So once you have done that, now we need the position that we are trying to solve the inverse kinematics for. So let me write it here. Okay. I'm going to say P for, I'm going to write it, set it up here. These are values that I have used, but obviously in your worksheet, you'll have different values to solve, which is like this, right? I have a set of values like these. So for me, P for the end effector. Okay, so I'm going to write P here as, let me write it as capital P. So the first three values will be position. So in my case, it is minus 3.0052, 6.1872, and 2.7016. Okay, this is the position. The orientation will be here in degrees, 78. this is my position and orientation of the first three values represent the position, the final three represent the orientation. So I want to split this. So what I'll do is, I'll basically write it as position will be equal to P of 1, 2, 3, the first three elements. Okay? P of 1, 2, 3, and orientation will be equal to P of 4 to 6. Okay? So the last three refer to orientation. But there is one problem. The orientation is given in degrees, we need it in radians. So what I'll do is, let's first see if the split is correct and then we'll change it to radians. So I'm just going to run this. Okay? And let's go to the window and see that the values are split properly. Okay, this is the position and this is the orientation. Now I want to convert the orientation to, I'll pull this up from here. Actually, let me move it down, or let's keep it there. Okay, that's fine. So I'll convert this to radians by pi by 180. Okay, so this will be, here I'll comment it and I'll say orientation angles in radians. Okay, so we have the orientation angle in radians. Okay, so what is the first thing that we do? We have to set up the R06 matrix, right? We want this so that we can compute OC. O is given to us. O is this point. P position is the O. Position is the end effector position. So we need to do, so we can subtract this, okay? So let's do this. First step will be to find this, okay? So that we can use it in this equation, okay? So this is, let's call this R06. Okay, or simply R, whatever you want to do. So R06 will be Euler of these angles. So first, let's construct the final orientation matrix. So I'm going to write here. Let's call it step 1. Okay. End effector orientation matrix. R06. Okay? End effector orientation matrix R06, which is basically constructing this based on Euler. So what we'll do is we'll say R06 is equal to Euler of, okay, EUL to rotation of the orientation values. So this will be ORN. Okay, what will this do? Let me explain here. This will give you an R3 by 3 matrix. This command, Euler, EUL to R, that means it converts Euler angles to a rotation matrix. You give the angles here, which is phi, theta, and psi. It will give you it will return a R3 by 3 matrix. Okay, an R3 by 3, which belongs to special orthogonal group 3. Okay,
Belongs to what?
special orthogonal group. It's an orthogonal matrix, SO3. Okay, we studied that. All right. So let's look at the matrix. It's good to run it once so that we don't end up with a million things we have to debug in case things go wrong. So you have R06 right here. Okay, if you run it, you'll see the R06 matrix. Okay.
Professor, can you go up a little bit?
Please make sure that you have multiplied by pi by 180. Otherwise, you'll get it. You'll assume everything in degrees. It has to be in radians. Okay. Now, what we'll do is we'll try to find the OC, the wrist center. So wrist center will be, this O is nothing but our position, POS. So this will be POS minus this. Okay, so let's do that. I want you to write the equation. Just write out the equation, wrist center. I don't know, I want you to try setting this up. Will be equal to POS minus D6 R03. Write this in MATLAB. Code that in this equation so that we all, and then we'll double check. Okay, so step 2 is find the wrist center. Find the wrist center OC. Huh? I'll talk to you. Is it a yes or a no? Or it's a maybe?
It's a maybe towards the yes, but the problem is okay.
Are we done? So let me write this and you guys can check and you can tell me if you got the same thing, okay? So OC will be equal to minus, obviously we have to give this as POS times, we'll give this as 3 because your D6 is 3 times, right? Here we can write this as R06 times 001 because it's a column matrix. Okay? The reason I use apostrophe is because it's a column matrix. Here, let's write down comma. D6 is equals to 3. Okay. All right. So once you find this, what we'll do is we'll run this and see what, let's make sure that there are no errors here. So let's run this. And here you should get your wrist center like this, OC as so. Okay. Now you know the wrist center. That means you know the coordinates of, we know the coordinates of this point. So now, from here onwards, from OC, we need to find what is theta 1, D2, and D3. Okay? From OC, we need to find inverse kinematics using 3 terms. So let's find, so step 3 is find theta 1, D2, D3 using OC. Okay. I have given you the formula for finding theta 1 from here. In your sheet you will see these 3. Right? Set them up so that you can find theta 1, D2 and let's do that. Your handout has theta 1. Below the table, you should see the formula for.
Sorry? Display what? The matrix? What matrix do you want to display? Yeah, you just remove the semicolon. It will print.
This one? Oh, yeah. Yeah, you have to just run it, right?
No. Which matrix do you want to?
The very first one with
Correct. It's right down.
yeah, the same thing.
No. Just you have it here. You just put the semicolon over there. Put the semicolon over there. Try it now. Just right now.
Done?
Save it.
Okay, set up the theta 1, D2 and D3. Alright, so now how do we find x, y, z? X, y, z are the first three elements of the position, right? Position of 1, 2 and 3 will be x, y and z. So if you look at theta 1 will be equal to, let's call it as T1. Inverse tan is A tan. So we'll do A tan, okay, A tan. Now we want to divide, what is this, negative x over y. Okay, so negative x is the first thing. So this will be POS of 1 is x, because the first part is x. Okay, so when you have three values in position, let's say 5, 7 and 3, this is x, y and z, right? This will be position of 1. Okay, so we'll take that divided by okay. Fine. Now, next thing is, what do we do with here? Now this will give you a angle back in radians. It will not give you back in degrees, it will give you in radians. Let's go to finding D2. D2 is z minus 1. So that will be position of 3 minus 1. And D3 will be equal to square root, so we'll write it as SQRT of position 1 square. So we'll write this as